A lot of you probably know that the 3x3 Rubik's Cube has over 43 quintillion different permutations. But why is that? And how can you use that to find the combinations on a 2x2 or a 4x4? And how on earth are we going to figure it out if it's not a normal n by n, like an FTO? In this video, I'm going to go over all of this and more, and hopefully by the end, you'll be able to calculate the permutations of other kinds of twisty puzzles. But first, let's start with the basics, the 3x3. The way we will calculate this is by first splitting it up into different piece types: centers, edges, and corners. We can do this because these pieces will never switch spots with each other. There will never be a corner here, and there will never be an edge here. Centers are fixed in place and won't add anything, so let's start with edges. There are 12 of them, so there are 12 edges that could go in this first spot. Now there are 11 edges left. So if we pick a new spot, there are 11 edges that could go there. Then the next slot has 10 edges that could go there. Do you see a pattern? This will equal 12 factorial. Each edge can also be flipped in one of two ways. However, it is impossible to have an odd number of flipped edges. After all of the other edges have been chosen, the last one only has one possibility. We have to take away a 2, and we multiply 12 factorial by 2 to the 11. Next is corners. Similarly to edges, we can find the number of corners, 8, and then do 8 factorial. Corners can be twisted in one of 3 ways, so we multiply by 3 to the 8. But again, we can't have a single twisted corner, so we have to take away one of those 3's. We're left with 8 factorial times 3 to the 7. So now we multiply these two equations together and we're done, right? Well, almost. There is one extra kind of impossible state on this cube that we will have to divide out of our number. You can't just have 2 swapped edges or corners. Because of this, half of our states are illegal. This means we have to divide our original number by 2. This is our final equation, and our answer is just over 43 quintillion. Now let's use what we know to find the amount of permutations of other puzzles, starting with the 2x2. To start, we can take our corner equation from 3x3, 8 factorial times 3 to the 7, as corners move around the same way as on a 3x3. We no longer have to worry about dividing by 2, because J-perms swap hidden edges that don't matter in the solve. Is this all? It looks right, until you realize that we're overcounting. How? We're counting this and this as different scrambles, even though these are the same thing. We can easily fix this by dividing by the number of ways we can hold the cube. We can pick 6 sides for our top side and 4 adjacent sides for our front side. This gives us 24 orientations of a cube. We divide by 24 and we get our final answer of about 3.6 billion. Now what if we go up? Let's take a look at the 4x4 Rubik's Cube. This has many more pieces than a 3x3, and it has 2 parities. How would we do this? Again, let's break it up into its 3 piece types: centers, wings or edges, and corners. The formula for corners is the same as on 2x2. They function the same way, and we can still have 2 swapped because of PLL parity. Additionally, neither puzzle has a fixed orientation, so we can divide by 24 again. So let's go to the centers, which are no longer attached to the core. There are 24 center pieces, 4 on each of 6 sides. If we use the same logic that we did for the other pieces before, we would get 24 factorial, which is a very big number, over 620 sextillion. Again, this number overcounts, in a different way. There are many identical pieces, so we have to divide them out for every way they can be swapped. There are 4 pieces of each color, and the way to arrange 4 objects is 4 factorial, or 24. There are 6 sides, so we will divide by 24 6 times. The final pieces now are the wings. There are 24 of them, so again we do 24 factorial. Unlike on 3x3 where you can't just swap 2 edges, on 4x4 you can get parity, which occurs because of an odd number of slice moves. And because of this, we don't have to divide by 2. Wings also cannot be flipped like edges, so no multiplying is necessary. So putting everything together, here's our final equation, and we can simplify it to get this crazy number here. Just to put this into perspective, I found an article on the rubikzone.com that said if you had that many teaspoons of sugar, you would fill the solar system out to 3.5 times the orbit of Pluto. That's just insane. What's even more insane is that it would weigh about 70 times as much as our entire galaxy. Yes, 70 Milky Ways is equal to just one 4x4 Rubik's Cube. Now we start to see a pattern. For each cube, we split it up into individual piece types, take the amount of each piece and find the factorials, and finally divide for any parities, identical pieces, or unfixed rotations. Let's try this on the 7x7. It has 10 piece types, 11 if you include the fixed centers. If we start with the 6 center sets that can move, we can see that each kind will have the exact same equation as on 4x4. There are 24 total and 4 identical ones on each side. This makes things a lot simpler. I wonder if we can find a similar pattern on the edges. And we can. The 2 outer sets of the same equation, which also works just like the 4x4. We get 2 sets of 24 factorial. The inner edges and corners are the same as on 3x3, which is actually how the puzzle is physically designed. There's an inner 3x3 shell, and everything else stacks on top of it. So here's our final equation. And our final number is over 19 duoquinquagintillion. I didn't even know that was a word until I wrote this script. Okay, so n by n's weren't too hard, so why not try other kinds of puzzles? Let's start with the Pyraminx. First, we'll do the edges. There are 6 of them, so we can do 6 factorial to randomly arrange them. However, when we do a turn, we're always cycling 3, meaning 2 can't be swapped. Half of our cases are now bad, so we'll divide by 2. They can also be flipped one of 2 ways, so we can multiply by 2 to the 6. But remember, we can't have one flipped edge, so we remove a 2. Alright, not too bad, let's move on to centers. They're fixed in one spot, but they can still rotate in one of 3 ways. There are 4 centers, so we have 3 to the 4. Tips are actually the exact same, so we have another 3 to the 4. Multiply all of this together, and we have a bit over 75 million, which is a bit more than we had on 2x2. This next one's an interesting one. This is the Rubik's clock, and the pieces only rotate in place without switching spots. Yeah, no, this one's pretty easy. Each piece can be in one of 12 orientations, and there's 14 independent pieces, so it's just 12 to the 14. If you count pins, you can multiply by 2 to the 4, but the WCA doesn't care about pins anymore, so I won't count them. We end up getting just over 1 trillion combinations without pins, or about 20 trillion including them. FTO has 2 orbits, meaning some pieces can't swap with each other. So some of the calculations might be a little different. Let's split up the pieces again, starting with triangles. There are 24 of them, yet again, but some of them can never go in the place of others. This is because of the orbits. We instead have 2 separate sets of 12. Each side has 3 triangles, so the equation is 12 factorial over 3 factorial to the 4 for the 4 sides. There are 2 orbits, so we can square our equation. Next up are edges. There are 12 of them, and we can't have 2 of them swapped. The edges can't be flipped either, so we're done here. There are 6 corners, again 2 cannot be swapped, and each one can be flipped 180 degrees. We can't have an odd number of twists, so we only have 2 to the 5. Putting together our 3 piece types, and this is our final equation, right? Well, just like 2x2 and 4x4, we have the same problem. There are no fixed centers. We can fix this by dividing by all of the duplicate orientations. We can pick from 4 sides for the top, and the 3 remaining ones for the front. I'm not including the other orbit because again, the pieces cannot be swapped, and we would end up undercounting. 4 times 3 equals 12, so we'll get about 31.4 sextillion. Let's finish with the trickiest one, square 1. This puzzle is very different from the others because it shapeshifts, the only one to do so in the World Cube Association. The edges and corners can take each other's places, so how are we going to be able to calculate the combinations? If you want, you can pause right here to try and figure it out. One way we can do this is by finding the number of non-shapeshifted combinations first, and then multiplying it by the number of different cube-shaped cases, or the number of shapes the puzzle can be in. The reason we can do this is because each of them is just a non-shape-shifted scramble, plus an algorithm to get to the final scramble. Each of these cases corresponds to one cubic state. There are 90 cases, so we can just find the number of cubic states and we're done, right? Not exactly. These 90 cases also have different sliceable ways the top and bottom layer can be aligned. So there's two ways we can calculate this. The first scenario is if we don't care about the orientation of the U and D layers. We can still use the 90, but we also have to subtract out a bunch of the square cases, because these would be the same scramble. The WCA counts different orientations of these layers to be different scrambles, so this won't work. We will have to do this a different way. In our second scenario, we do care about the orientations, and so we will just multiply our cubic number by the total amount of sliceable orientations. This number would be 3,678. Alright, now we can split it up into edges and corners for cubic states. There are 8 of each piece, and there is no flipping or twisting, so we get 8 factorial for each, or 8 factorial squared. Parity or 2 swapped edges is possible, so no dividing is necessary here like we've had to at the end of 3x3. The equator, or this middle section here, can be flipped, so we'll multiply by 2 for its 2 possible states. We multiply our 3 terms together for a final product of about 12 trillion. Okay, that was a lot of numbers. If there's another puzzle you want to know the combinations of, I'll be starting a series of shorts where I'll explain some of them, so let me know in the comments. And if you enjoyed this video, please hit subscribe and tell me what kind of video you want to see next. See you all in the next one. Bye.